Welcome to The Explainer. Today we're going to get into a really cool research paper that totally rethinks the solar panel by tackling one of its biggest hidden flaws with a surprisingly elegant solution.
So let's zoom out for a second and look at the big picture. Solar energy isn't just growing, right? It is absolutely exploding all over the world.
And it's the scale of this change that is just, well, it's mind-blowing. When you look at the data from the source paper, you see this isn't just some gradual increase. We're talking about exponential growth here.
Yeah, check this out. The paper points out that total capacity grew more than 50 times in about a decade. 50 times! That is just a staggering expansion. It's really cemented solar as a critical piece of our global energy future. But, like with any tech that grows this fast, there's always a catch. There are always little inefficiencies hiding under the surface. And for solar, the problem is literally baked right into how it works.
So, here's the irony. It turns out that a solar panel's biggest strength, all that intense energy from the sun, is also one of its biggest weaknesses. Why? Because they get hot. Like, really hot.
And here's the core issue, right? As a solar panel gets hotter and hotter, its efficiency actually drops. So you can have the same amount of sunlight hitting it, but you get less and less electricity out of it the hotter it gets.
Think about that for a second. All of that heat that's just building up on a roof, that's energy. It's energy the panel just can't turn into electricity. It's just radiating away, totally wasted. It's a huge source of waste, really.
Okay, so what if we could actually grab that wasted heat and do something with it? Well, that's exactly where this research comes in. They propose this really clever, integrated solution to turn that weakness right back into a strength.
Okay, so the first part is the bit we all know and love, the photovoltaic cell or PV cell. This is the classic solar panel tech. It's the workhorse that does the main job of turning sunlight into electricity.
But then they add this other really cool piece of tech, a thermoelectric generator, or TEG. Now, a TEG is fascinating. It's a device that can create electricity just from a temperature difference. If one side's hot and the other side's cold, boom, you get power.
So how do they put these two together? It's pretty brilliant. Sunlight hits the PV cell on top. It does its thing, makes electricity, but it also gets hot, right? Well, that waste heat, it flows straight down into the TEG layer underneath. And that TEG uses the heat to generate more electricity. It's like a 2-for-1 deal on sunlight.
And this is the really key part, the secret sauce, if you will. It's the integration. This isn't just, slapping a TEG on the back of a solar panel. It's designed as one single, seamless unit. By getting rid of any gaps or extra layers, they make the heat transfer super efficient, which boosts the overall power and could even cut down on manufacturing costs.
But of course, designing something like this is never that simple. The researchers basically had to solve this tricky engineering puzzle, a real Goldilocks problem to get everything just right.
Okay, so this is where it gets really interesting. Inside that TEG, you have these little things called semiconductor arms. Now, if you make those arms longer, you get a bigger temperature difference, and that's great for the TEG. It makes more power. But, and this is a big but, it also traps more heat up in the main PV cell, which makes it less efficient. And if you make the arms shorter, well, the PV cell stays nice and cool and happy, but then the TEG doesn't get as much heat to work with, so it makes less bonus power. See the dilemma?
So what do? They ran a ton of simulations, crunched all the numbers, and they found that perfect Goldilocks sweet spot. This table here shows that optimal design, the exact arm length, the area, the spacing that gets you the absolute maximum total power from both systems working together in perfect harmony.
All right, so after all that super careful engineering, all that work to find the perfect balance, what's the payoff? What did they actually find? Well, the results point to some seriously exciting uses for this thing in the real world.
Yeah, the main takeaway from the research is super clear and powerful. The integrated design flat out works. It delivers more power and has a higher efficiency than a regular old solar cell all by itself.
So how much better are we talking? Well, the paper points to other studies that show this kind of hybrid setup can boost total efficiency by anywhere from 8 to 23%. Now, that might not sound like a huge number, but in the world of solar, that is a massive leap. Every single percentage point is a huge win.
And the researchers really zeroed in on two areas where this tech could be a total game changer. First, in big solar collector systems that already use water to cool them down, that would make the cold side of the TEG even colder, which means even more power. And second, and this is really cool, in outer space. You've got the perfect setup out there. super intense sunlight on one side and the freezing cold vacuum of space on the other. It's like the ideal environment for this device.
You know, when you step back, this whole idea is so much bigger than just a better solar panel. It's this powerful reminder that there is wasted heat literally all around us, and it's this huge untapped resource. It really leaves you with this incredible question. What if we could start capturing that waste heat everywhere? From our cars, our computers, our factories, and just turn it all back into useful power?